Great, hi. I'm Brandi from Unity. I'm joined here by Micah, who's my Google counterpart. And we're really excited to talk about connected games today, specifically real-time multiplayer games. I've been passionate about making games that connect people in unique and exciting ways for many years. And I've been from Bungie all the way to an indie called Phenomena, and I've seen just how hard it is to be able to make these kinds of games and to succeed with them. In the last talk, we had a lot of cats, and there won't be as many this time, but we covered the breadth of what we're referring to as connected games, all the way from dynamic single-player games to turn-based multiplayer games to real-time games and persistent game spaces. And at a very high level, we covered some of the problem space that you'll encounter as you try to get to these different levels of connectivity in your game. And today, like I mentioned, we're focused first on the core real-time multiplayer tech. How do you get people connected and transferring data as quickly as possible so it feels like a really fast and responsive experience? So I should also note that this is just the beginning of an entire track of talks that will go into a lot greater detail from here. So we're going to talk at maybe a medium level of technical detail, and this will act kind of as a primer to the following talks that come after this, that are going to be covering all kinds of networking concepts to scaling servers and using a matchmaker to tie all of that together. So first, let's talk about some of the core challenges that real-time multiplayer games all face. So first is latency. Just how responsive does this game have to be for your players to have a good, consistent connection quality? And scale, how many players do you want to have in the same game space as you at the same time? Security, how easy is your game to hack? And does it put any other users' machines at risk? The cost, can you achieve a reasonable cost per user so you can reach profitability? Complexity, how complex is the entire technology stack and how much engineering work is going to be required? And then reach, how many people are you able to get into your game and will be able to use it? There are a lot of trade-offs in this tech, and the first thing to focus on is all of the core components that are required to achieve these different goals. And a typical stack for a real-time game looks something like this. And it may not have all of these components depending on how you make it. But it starts at the baseline with a network transport layer. It's the piece that communicates most closely with your hardware. It's sending the bits back and forth over your internet connection. On top of that is your client and server runtime, which is typically what you see with Unity. You know, Unity is your game client runtime. It could also be your server runtime. It's all the additional code that's happening on your client and server. And then the next layer up is all of your services and server management. So if you need to match people together, or if you need to have an identity service so you can uniquely tell which player is coming in at each time and have stored information about them. As well as if you have game servers, which we'll talk about why and when you want those, managing those servers. Are they hosted somewhere? Are they staying up? Are they getting updated when they need it? So the stack can get quite complex. And when we talk about network topologies, that's the concept of which of these pieces exist and how they're all tied together. So we're going to start first with going through an array of different kinds of network topologies for real-time games. The first is the simplest. It's your local couch multiplayer, because everybody is sitting on the couch together, they're playing on a single machine, and from a networking perspective, it's definitely the simplest. All you have is a client runtime. It's literally just the same way you're making your games today. You're just processing multiple inputs. The beauty of this is that there's literally no network latency. You don't have to send any bits anywhere. And you don't have to really worry about security or cost or complexity. It's almost no harder than building just a normal single-player game. The downside is that if everyone's playing on the same machine, typically you don't see more than about 4 people at a time, especially if it's split screen, because trying to see your little bitty character about that big is not a super awesome experience. And then reach, you're only limited to people who are up for playing real-time games together. So the audience may not get as far. Next is LAN. And I'm only adding this because it's become more and more popular recently for XR installations. So if you want to go have a really immersive experience, you need very low latency because, like people have experienced in VR, if there's very much lag or anything is noticeable, you might get sick. So there's these super cool ideas of putting people into a space together and having it feel really immersive and have everything around you be networked and be with other people in that space. And for that, people are typically using a LAN connection. And depending on the scale of it, typically using a hosted server there on site that doesn't use any internet at all, but it still has to connect multiple different devices. Whoops. Now, this has also similar scorecard to your local games. And in this case, you can get to significantly higher scale. You could hit, with a good beefy server on site, hundreds of players all connected together. The downside still is reach. Everybody has to be co-located. So it's kind of specialized use cases that you'll see this come up. The next is peer-to-peer, and I have it broken down into 3 variants because I've noticed there can be a lot of confusion about how different versions of peer-to-peer work and what some of their trade-offs are. The first tier is just direct peer-to-peer. It assumes every one of your players is trying to directly connect to each and every other player. It's sort of the most straightforward, but actually it puts the most processing challenge on each of those clients. Because each client is trying to take n different inputs from however n many players you have trying to connect and process all of it at the same time and keep it synchronized somehow. And each client is responsible for that. And the logic for it is surprisingly challenging. The next variant is to do a client-server host. So it's the concept of taking one of your players and turning their game client into a client server. So everybody just connects to that one client, that one player, and it centralizes the traffic. The downside is still that that one player now is the only one having to process all of that data, and they can get what's called a host advantage because they're not having to pass data over a network. They get literally no latency while everybody else does get it. Also, if your host decides to rage quit, the game either drops or you have to migrate everybody somehow. And host migration is not only really hard to do, it's a terrible user experience. Because all of a sudden the game has to pause, you have to reestablish connections for a new host to everybody else, and then somehow get everyone back synchronized and start again and hope it all works. And it's bad for the players, and it's a pain to build it. And then the last, which is actually what our prior technology stack included, was a client-server host with a relay. In the prior 2 topologies, you're still hoping that the players can directly connect to each other, which with firewalls is a surprisingly hard problem. Even with NAT punch-through, the estimated reach is about 80 to 90%. So somehow, for those 10 to 20% of your players that are still going to have a bad experience, you have to have a way to get through to them, which is typically done through a secure service relay. It's just literally relaying the data back and forth. The downside to this is that it adds latency. So if your player over here is sending data first up to the cloud to some service somewhere, then sending it to another client, then it has to go back up and around. Suddenly you're in your worst possible case scenario for latency because that data just has so much further to go. So I know this slide is super complex, but it'll be here for you in the future, if, in future recordings and stuff. So I'm just going to call out a few key points about it. With peer-to-peer, there really is no silver bullet. For the vast majority of different kinds of games, a peer-to-peer model is going to be very hard to succeed with it. Latency will always be inconsistent. Sometimes it's great, sometimes it's poor, and sometimes it will drop out completely. Security is a big challenge, because in any case where your game is even moderately successful, if your code is all running on a game client, it will be hacked, and you will be trying to play whack-a-mole to try to figure out how you keep those people from making everybody else's experience worse. Scale is another big challenge. So when you're dependent on just a game client's hardware and bandwidth, like even if it's a pretty reasonably powerful game client, someone has a beefy PC and a good bandwidth connection, you're still limited to maybe 10, best case 20 players together. So if you aspire to get a lot more people into the same game session together, you're going to hit inherent limits until you can actually control the hardware that's hosting that connection back and forth to your players. And cost isn't actually free. If you want low latency in a peer-to-peer network, you have to find players that are located close to each other. Because if they're across the country or world from each other, they're all going to have really high latency. So you need a matchmaking service to find people that are located close together. And like I mentioned, if you want to reach everybody, you have to have some sort of relay service to get the information back and forth. So it isn't actually as free as it seems. And finally, none of these are easy. Like I mentioned before, keeping n players in sync in the direct peer-to-peer case is hard. Or if you have a client host, then you have to deal with this host migration problem. So the last topology is the dedicated game server model. In this model, you use hosted servers that you control. So they're never in the hands of a player. And you can decide just how beefy you want it to be. You can decide how many of them you want distributed around the world. You have full control over how fast and consistent your player experience is. In this case, you can also even make the logic that's running on the server be fully authoritative. So whenever cheaters come in to make the game experience better for themselves and worse for everyone else, you have a lot more control over it. So to note here, the dedicated server model really does provide overall the highest possible quality with fast connections. You can hit hundreds of players of scale depending on how well your servers are able to run. You can get good cheat prevention, global reach. The two challenges that are worth noting are costs. So now not only do you have these game services that, always available game services are not free, you also have a dedicated game server, which is also not free, because you've got this thing running in the cloud or on some on-prem situation. It's stuff that you still have to figure out how to pay for. And the second piece is that you need this full stack, this entire software stack from all of the transport layer all the way up to the server management and hosting. And then the summary of all of these is that I think there's kind of a few interesting things to take away from this. I think local and LAN games are surprisingly undervalued, and that's just my opinion. But they're a really fun starting point. It's a nice way to start feeling out what it means to design games and play games with other people without all of these extra headaches. And I think that in peer-to-peer, the worst about it, and the thing that we learned, was that a lot of the challenges there are inherent. Like we as Unity, there's nothing I can do to make a consumer's hardware better or faster or have more bandwidth. And if the code is on your client, there's almost nothing you can do to stop it from being hacked. And so when we tried to look at our existing solutions to make them better or actually make them help people succeed, we realized we were running out of options. So we're focused on dedicated game servers because the two challenges on it, the complexity and the cost, are things that we can work on. They're things that we can provide more and more pieces of this stack so that you don't have to build everything yourself. We can work on finding ways to get costs down. Like those are problems that you can actually make progress on. And so we're focused there today. I'm going to hand over to Micah, who's going to start talking about some of the core concepts of what we mean when we say real-time game communication, so that when you're going through some of the future talks today of exactly how we're approaching some of these pieces, you have some of the terminology that I think a lot of people who have been doing this for a while may already know, so bear with us.
Thank you, Brandi. So real-time is kind of straightforward, right? Anyone who's played any kind of first-person shooter or real-time game like that expects that when you click, tap, or pull a trigger, something happens promptly in real time. It feels like it just happened. When we talk about latency in real-time games, we're really talking about that responsiveness, which really impacts gameplay and the engagement of your players. If you look on the left, you see that the game is a little bit more sluggish. Things aren't moving as responsively versus the right side. And that's just a simple difference between how many updates are being delivered back to the game. So you have a bunch of taps happening, and how quickly are we responding to them. I think that the right side actually looks a lot more like it's real time versus the left side. When we break latency down, we're actually talking about kind of 3 different tiers Just for level setting on the vocabulary, when we talk about the client side, we're talking about frames per second because there's rendering happening. And when we talk about the dedicated game server side, it's headless and it's doing simulation, so we talk about tick rate. But it's really kind of the same concept of how quickly are we turning around the next frame, the next update. So on the client side, this is a typical scenario, by the way, for like a first-person shooter type game of how you would configure things. But this isn't like a hard and fast rule. You'll do what's right for your game. You might have a higher frame rate or a higher tick rate or vice versa. So on the client side, what this translates into is the client has 16 2/3 milliseconds to be able to process its work and send some event up to the dedicated game server. Once it hands things off, then it has to go on the network. So the network is a variable, right? You don't have any direct control over all the different hops that happen between your game client and the dedicated game server. So in this case, 25 milliseconds is actually a really good latency for the network, but that can drastically change depending on what country you're in, what ISP the game player is on. Is someone watching a movie streaming over the network at home while they're playing? There's lots of different variables that you can't control for. So in this case, we're assuming pretty good latency. Then we get to the server, and at the server, we're allowing some leeway so that we can accommodate variances from the client side. Maybe someone didn't get their update to us in time, so we have a little bit more time to process the ticks on the server. So that's why there's a bit of variance there. So the overall round trip time actually amounts to the equivalent of 7 to 10 frames of gameplay. So that's actually a significant amount to deal with. So there's a lot more that goes into the game design to mitigate what that impact could be. When we think about networking too, we're thinking globally, right? I can tell you that from Google's perspective, we have a global private, like we own our own global network that's all fiber optics. So it's lasers shooting all around the world, but we're still limited by the speed of light. So we can't just solve it with Google's super fast network. It's a really solid network. But in this case, if you were to put a player in a different continent, they would have a disadvantage over the players who are closer to that dedicated game server. So what we do is we mitigate these concerns by placing the game servers closer to the players. And there are other things that we can do to bring the players together globally, perhaps on the database level. But in this case, this sort of is a forcing function on how you design dedicated game servers. And it matters where you can place them. So I'm going to hand it back to Brandi now to do a little bit more of a drill down into the rest of that stack from the topology we were just talking about.
Great. So assuming that we do a dedicated game server topology, we need to solve all of these different portions of the stack. So we're going to work from the bottom up and give at least some key concepts that are helpful to understand and some of the trade-offs about how you may want to think about designing or creating these things, and give a little bit of context about the way Unity is approaching it, so you can make decisions about whether or not you may want to get on board with some of the future products and services that are en route. So starting with the network layer, it's important to first understand what we mean when we say connection. So like your home has an address, each of your devices have an address, and it's called an IP address. So anywhere on the network, you can uniquely locate that device with that number. And on the device, you have a number of ports, and those can be bound to a particular service. So whenever you look at it, it's sort of the address of saying, I need to talk to this service on this device, whenever I say I have a port and an IP. So whenever you establish binding a socket, it means that you are saying that this port on this device is now connected to my game client, and it's now going to be able to communicate out to whatever is the bound socket on my server. And a socket is literally just the IP and port combo. Like it's the reference of that unique identifier. And when we talk about communication, we have this concept of packets. It's the information that's sent over the network. And some portion of it is header, and some portion of it is payload. And the proportion varies depending on the protocol that you use. With TCP, the header is going to be larger because it's trying to do more for you all the time. It's going to make sure you get guaranteed message delivery and that the ordering is maintained. But that means that it is slower. It has more overhead. whereas UDP is going to be faster, but if you do need things like reliability or you need the ordering to be enforced, then you have to put that into your own game client logic. So Unity is focused on a UDP model, and these are some of the core goals that we're thinking about. And I should note that Tim is around here somewhere, and he's doing a talk right after this to get into a lot more detail about Unity's new transport. But I'm going to give a few quick high-level goals just so you get an idea of what we're thinking about. So in the top chunk, it's all about establishing those connections, making sure communication is happening and the packets are getting generated and sent over the network, and that we're doing so with the best possible performance. So using a UDP-based model, and also thinking about how the transport can speed things up in the client and server processing itself. Can it support multi-threading and do all the things that should be possible in the new version, in the new engine features we've been building? And of course, platform compatibility. Like I said, the transport lives at the very bare bottom. It's the piece that has to understand how you do communication across a broad range of devices. So the transport is ultimately responsible for making sure it can work across whatever devices we ultimately want to network. And then modularity and transparency just means that you shouldn't have to pay the latency overhead for features that you don't need. So for modularity, each feature that we ship down the road will be pieces that are just separate packets, so you can choose to include them or not. And because they're packages, we can provide them full source. So you can see everything that's happening in them, you can debug and step through, you can figure out exactly how you make it work better for your game. And the next level of the stack is the client and server runtime. We mentioned briefly before the concept of a server authority. So whenever you're running your game, you want to trust as little as possible about what's happening on the game client, which means you're only going to send pretty small packets of essentially just the inputs. What buttons have they pressed? What are their thumbsticks doing? Trust as little as possible, and send that to the server and simulate basically the entire game as much as possible there, and then send a full packet of game state data back. Now, the downside of this is that you are waiting for quite a while on the game client to get an update. So whenever we think about what the runtime is doing, the game client is thinking about how it compensates for waiting. Those 7 or 10 frames that you're rendering without new data, what do you do? How do you keep it feeling smooth while you wait? And on the server, it's handling the authority. You need to make sure you strip out rendering and audio and keep it as clean as possible so you can focus on simulating those n numbers of players that you want connecting all together. And it's also responsible for talking to the hosting environment. So if multiplay is monitoring servers, they're out there saying, are you alive? Are you doing something? Can I kill you? It's responsible for communicating back and saying, no, please, I'm good. Or no, actually, I'm frozen or crashed. So there's some stuff that has to be running there too. Peter, who we announced this FPS sample game yesterday at the keynote, is doing a talk in a couple of hours in this room where he's talking about the net stack that does all of these things with a very specific implementation. And he'll be here to walk through that in a lot more detail in a couple of hours. All right, and then I'm going to hand back off to Micah to go through the top of the stack, the services and the server management.
So we're going to talk a little bit about planning for the infrastructure and some of the other decisions that flow from that. There's actually lots of different paths that you can take. Typically, you might end up with kind of a hybrid approach, working towards something as you scale up. So when we talk about infrastructure first, who's going to be in charge of the hardware? Who's going to pay for the hardware and maintain it? Is your hardware going to handle the success of your game as it scales up and so forth? So on the on-prem side, meaning that you're hosting your own hardware, maybe you're leasing some servers and running your dedicated game servers there, or maybe you just have a server in the closet, kind of a scenario, or in the garage. And that would be fine for development testing and maybe some early betas, but at some point, as we mentioned earlier, you want to bring the dedicated game servers close to your players, so you'll need to be in more places. It's harder for you to be an expert in data centers because that's a capital-intensive investment. You'd have to buy a lot of locations. That happens to be what cloud providers like Google Cloud specialize in, so that's the trade-off. the cloud infrastructure from Google Cloud would give you the opportunity to place dedicated game servers anywhere those data centers for Google exist. And all the scaling and capacity planning are done for you, which kind of leads us into like the services side, like who's doing what. This is just to give you an idea of the actual hardware. And you might start off with owning your own and gradually go towards the cloud, or you might burst into the cloud, which is what we refer to of when you need lots of capacity quickly, then you have an option to send it over there. But when it comes to managing the services, can't tell if I clicked or not. I'm gonna try again. Okay, there. So this is also sort of like who does the work of maintaining things. Typically when we talk to our game developer friends, people are generally interested in making games, not in becoming experts in the IT infrastructure. That's sort of a necessary evil to be able to successfully launch the vision you have for your game. But there is still the need for someone to manage those on-prem servers. So those would be unmanaged services, meaning that there's no one else helping you with them necessarily. You're probably doing the maintenance yourself, powering things down, applying patches, or not applying patches is probably more likely. But when you have things running in the cloud, one of the other things you get is that those are managed for you. So as an example, those servers, like dedicated game servers, can get automatic security patches without taking them offline. We can actually migrate to a different server, update this one, migrate back to this server, and not go down. That's something that cloud knows how to do. So that gives us the ability to keep things running. So the availability, which we refer to as a service level agreement, and that's where we say we expect that this service will be available with 5 nines. That's like the gold standard of uptime, which is really going to be important for a real-time multiplayer game. When we go a little bit further into the services side and we actually talk about how are you communicating with those services, we're just doing a brief pit stop here on 2 popular approaches for setting up endpoints. So sometimes people think that they're choosing between REST or remote procedure calls, RPC. There's actually it's not an apples to apples comparison. So REST is not like a codified standard, it's more of a set of guidelines. That's why you hear phrases like RESTful. That's to sort of capture like the general sense of doing it this way. RPC is actually a much more standardized approach, and it goes a long way back to the early days of Unix, in fact, for distributed systems. And it's making a pretty big comeback because of cloud, and I'll talk in just a moment about what's happening with RPC and cloud, and also some of the use cases when you would want to consider RPC over something like REST. But generally speaking, REST is really good for these general use cases where I need to make a request, get a single response, and I'm done. So that makes it very flexible. It's easy to understand because it's based on HTTP verbs like get, post, put, delete. And it uses the standard HTTP error codes. So everyone can understand what those error codes are and translate them to some degree. RPC gives you all the customizations, but it's very high performance. The network stack for that is lower overhead. And one of the coolest things is that you can get streaming. So I can make a single request and then get an ongoing set of responses. Now I could think of several game services scenarios where that would be very desirable, such as matchmaking, where I say I want a match for my game. Is it ready yet? Keep feeding me a heartbeat, tell me what's going on. Like a stream of responses would be really nice in that case. So we'll talk a little bit about matchmaking in just a moment. And one other difference is in how you actually access those. An RPC endpoint is going to be very focused on being one thing and being really good at it, whereas REST will be more general. So that's why you see get all users versus just users. So there's actually a cloud native RPC implementation. I'm just going to briefly talk about it here. It's called gRPC. This is an open source project that is part of the Cloud Native Foundation. The general concept here is that you focus on designing the message structure at your service. So you say like, I'm only going to accept messages that have these things in it. So you're making a contract. And the cool thing is that when paired with protobufers, you can auto-generate the client-side libraries. So you simply made the service the way that it needs to be, and then across languages such as C# or Java or C++, lots of different languages. I think there's over 10 supported. You can just generate all these client libraries, and now you just call the classes, and boom, you're using your service. You can do the streaming and all that. So in this case, you see a single service that stood up. It happens to be based on C++, but it doesn't matter. It could be C#. And then you have different clients that are consuming the service. And in the bottom, you see an example of a client that's receiving multiple responses, which is the streaming in motion there, as we mentioned earlier. So streaming is kind of like our key point that we were thinking about for matchmaking. So I just want to talk a little bit about that as an example of a service where we might use something like RPC. And I also want to just broadly talk about what does it take to make a good matchmaker. And we're going to put in a little bit of a plug for our joint project, OpenMatch, and the managed version of that Unity just announced yesterday. So OpenMatch as a matchmaking project is meant to be flexible by default, like that's its priority. It won't decide what match logic you should have in the game. It's just going to be really good at scaling whatever match logic you end up using. And that's in response to the off-the-shelf solutions that tend to try to tell you, hey, you should probably pick from these few options of match logic. And at some point, a game developer will say, like, well, my game doesn't fit into those containers that you gave me, so I'm going to build my own matchmaker. So OpenMatch is basically our way of saying you don't need to build your own matchmaker. You can use that if you're in that position where you would need to roll your own. But what's cool about the Unity matchmaker is that it's based on the flexibility of OpenMatch, but it's integrated into the Unity ecosystem, which delivers all of this amazing ease of use opportunity as the features continue to roll out for the Unity matchmaker. So let's just, I'm going to have to point my clicker this way, I won't click. Let's just do a quick little overview of matchmaking. Like the traditional way of doing matchmaking is I have players. In this case, we're doing dedicated game servers. And there's some matchmaking server that we built that has our match logic. We're going to ingest the players that are queued up to have a match. And we are going to match all of those players and get them into game servers. That's it, right? Pretty straightforward. Not necessarily a very scalable solution because that matchmaking server could have some issues with capacity if the number of players goes up. So the way that we're approaching this new matchmaking project and what Unity Matchmaker is based on is this microservices approach. And so this is where the gRPC side of things comes into play. These microservices need to communicate with each other. So we have the part that you care about is the blue box there at the top. You create your custom match logic, and then all of the other infrastructure and scaling is done independently. So the front-end API that talks to the players scales independently of the back-end API that talks to the game servers. So anything at a given time could be adjusting and accommodating the load. But the end result is that you end up with players that come into the queue, and then this orchestrator function just makes sure that your match logic receives those players. They process those matches, put the players together as you had prioritized. Maybe there's some specific logic that you want, and if that fails, you just say whoever's got the lowest ping, something like that. And then you put the players together, and then we assign them to those back-end dedicated game servers. So this is the framework of matchmaking, and we're going to talk more about the Unity Matchmaker tomorrow in a session. As Brandi mentioned, this is part of a series of connected games. And now I'm going to hand it back to Brandi so she can talk to you about the actual Unity Matchmaker Alpha and what you'll be able to do starting today.
Great. Yeah, so yesterday in the keynote, we announced that because we know that to make these services and products and technologies actually work for all different kinds of games and real games, we need to start releasing earlier and often and be very responsive to feedback. So we are releasing this week everything we have across the board in its earliest, most minimal state so that we can be taking feedback every step of the way. And I'm going to walk through each of the components that are available and where to find them. And like we've said, there's going to be additional talks if you want to get in more detail as we go through. So the networking transport is available in a GitHub repository today. Inside of there is a transport package that is full source. It's unreliable based on UDP, and it does support multi-threading with the job system. All additional features are going to be released as additional packages ongoing in the coming weeks and months. You'll also find a really simple ping sample in that project, which has sample code for all of the rest of the stack that you'll also see, so that hopefully you can get it working with a live hosted game server and be able to measure your ping times back and forth. It's not actually a game, but there we go. The FPS sample is. So the FPS sample project is also available today, also in a GitHub repo, but the link there will route you to where you need to go. And this is the game that has not only the transport in use, but it's also showing sample full source for client-side prediction, interpolation, delta compression, lag compensation. All that stuff that we mentioned has to exist in your either game client code or server code to compensate for the fact that latency will exist. So you'll be able to at least see a sample implementation that works in a very real game scenario. In the server runtime, in 2018-3, the beta versions, you'll start seeing some workflow improvements for creating server builds. So if you go to Windows, if you go to Linux, you'll see this new option that says server build. And what that will do is it will make it headless, so it will stop it from running rendering or audio or all the things that you really never want to see running on your server. And it will respect what's called like managed define. So if you're using a hash-defined server that matches the Unity structure, then it will respect just the compiling and running the code that is specific for your server that you've defined to be as such. There will be more documentation around all of that stuff. Clicker, there we go. Then next is all of the services, and those we're rolling out more gradually. So there's an application form that if you go to that URL, you'll be able to sign up and provide a Unity project ID. And we'll be gradually onboarding more and more projects as we make sure the services are standing up well and responding the way we expect they will. So the first thing that you'll find is getting your game hosting servers set up. Oh, this is one step ahead. There we go. So the first thing you have to do is create a server fleet. What a fleet is just literally your grouping of servers that are designated for you in your project. So you'll go to this place in the developer dashboard and select a region. So you want to pick a region that's as close to you as possible, and then select Create Fleet. And then what that will do is it will provision your fleet over in the multiplay environment. It will link that to your UPID. It will set up a capacity of just one server for now, but we will grow that capability in future updates. And then it will sit there and wait for a server build. It can't start spinning anything up until it knows what code to run on the server. So the next step is getting your server build out to this server fleet. So in the cloud build UI, also in the developer dashboard, there's this build history page where you can upload a build that you've built on your own machine. Make sure it's Linux. Right now the only environment supported is Linux for the runtimes. And select the server option. And then once you have your build uploaded, you'll have this drop down with an option that says push to multiplay. It shouldn't say dev, that was a screenshot of the old environment. But anyways, push to multiplay. And then that will send your server build off to your servers. The notes to add here is that you do need that server query protocol. Otherwise, if the thing you're running isn't responding to the multiplay calls to it, it will think it's dead and it will kill it. So grab that from the ping sample that I mentioned before. There's some sample code in there to drop into whatever you're doing to make sure your game is responding to the environment. It does follow a specific naming and file structure, so the environment knows where to find the right build to spin up, so we'll provide documentation on exactly what that needs to look like. And note that this build will apply to your entire fleet. So if you have somebody already running on the server and playing something, it will blow them all away. So ask your friends before you push a new build. And then there's two options to allocate a server. So the concept is you have a fleet. It has some capacity available to it, right now just one. And if there's none left to allocate, then you'll just have to sit and wait. So there's two ways to allocate a server to your current game session, the way you want it, to make sure it's set aside for you. One is a manual method in the developer dashboard. So on the same page as you were on before, there will be a button called Allocate. And what that will do is it will go to your server fleet and say, hey, is there capacity? If so, okay, great, allocate it and give me an IP address to the server that you just allocated for me. And so in the dev dash, it will just send you back that IP address and port that then you can put directly into your code or game clients to connect directly to that server. The alternate option is to use the new Unity Matchmaker, which will help do that in a more seamless way instead of always having to re-enter that IP address. So in the developer dashboard, you'll go to the Matchmaking tab and tell it to enable. And that will take all those microservices that we just talked about, and it'll get a version of those spun up for you in Google Cloud. And it will return an address to the service. From there, you'll need to configure a player count. So what this says is, how long do you want the matchmaker to wait to go ahead and kick people into a match? And by how long, I mean how many players do you want to wait for before it kicks off? So if you're just testing it by yourself the first time, usually set it to 1. Hit configure, and it will then kick you into your server with just one person. Or if you have other people with a client ready to go and ready to hit matchmaking, then set it to however many you want it to wait for. Oh, and I forgot to note that this is not the end game. This is just the let's get the infrastructure working version. We have a lot of plans for latency-based matchmaking, skill-based matchmaking, and those fully custom match functions that we will enable through all of next year. Lots of different pieces of it coming online in various forms next year. And then once you have a matchmaker spun up, working, configured, you need to get it integrated with your game client. So in the ping sample, you'll see this demonstrated there too, but you'll grab that URI that's spit back out in the dev dashboard, and you'll integrate it into the matchmaking server attribute of your whatever game or sample you're working on. And then you run it. So you add a simple UI in the game to call the matchmaker. You'll select it, and then it will wait for the end clients to match. Then it will allocate a server, and then it will connect all your clients to the server. So everything just works behind the scenes, or at least we hope it does. And so that's everything for the alpha. The next question that we get asked a lot is pricing. And the downside is that I don't have actual set numbers yet today because we're still trying to figure out how much overhead we have to run on top of whatever we're running on Google Cloud. So we're doing everything we can to minimize that. So we don't want to announce a number till we know exactly where our costs are. But what I can tell you is a model that we're thinking about so that we can start getting feedback on the model. So during development, for alpha, we know people are taking on the pain of alpha technology and giving us feedback, and so we're not going to charge you for anything that's in alpha. It's, yeah, we understand that you're doing us a favor. Once we get it to a more stable place with more features, we'll move into a beta, which, you know, there will be some amount of server usage that is bundled with the Pro subscription. And if you're not a Pro subscriber, then we'll try to offer some really reasonable fixed price options to get started with very little risk, like you're not worried about incurring a bunch of costs that you didn't mean to incur. And then for production, we've all announced that we're allied with Google Cloud, and it's our goal to offer very similar pay-as-you-go pricing, if not exactly the same as what you see on Google Cloud today. The way that that works is that if you have no players in your game, then you don't pay for anything because there's no server capacity spun up, there's nothing happening. So you only pay when you actually have people playing your game. So if you have a lot of people playing, you have to use more infrastructure, but hopefully you're also making money off of the players that you have in your game too. So hopefully you're only paying when you're successful. So it's more of a pay-as-you-go model, and it's based on how much of the hardware you have to consume. So you're empowered to reduce even your own costs by making your code more efficient, by making your runtime smaller so you can run on a smaller machine, by lowering the amount of bandwidth that has to be required. And we know that that's a complex model, but we're going to also focus on making tools through 2019 that help you predict your costs more easily. So you can see how much, okay, I optimized my code, how much is my predicted cost per user now? So stay tuned for more about that next year. But we think it's still the right model because you're empowered to control your costs and you only pay for what you actually need. And just to reiterate, these are the rest of the sessions that are related to real-time multiplayer here at Unite LA this week. And we look forward to hearing any questions you all have. I think we still have a few minutes.
No, actually, I think we just ran out of time, but we can talk to
bummer.
folks right outside if anyone has
We'll
any
hang out
specific
outside the
questions.
door. Okay, thank you all so much.